So now we're getting into logarithms and kind of back to the theme of the class. You've done logarithms, but I want to make sure we're fully aware of why they exist and how they're used in here. So the first big thing to tell you about them is they're the exact opposite of the exponential equations we just did. So I'm going to dive in with just examples of why we have these things, because to me they were always kind of obscure and I never quite knew why in the world I was learning about them. So that's where I like to start, is here's why they exist in the first place, so you at least have some kind of context to think about. So this is the decibel sound system. That sounds weird. But this tells you how the decibel, when you hear like how loud something is in decibels, how that works. So the scale's measured in kilopascals, which is basically an amount of pressure. So the way to think about that is when something really loud hits your ear, it actually puts a lot of pressure on it, which is indirectly force. So it actually, that's why it hurts your ear, because it's actually pushing so hard on your ear that it's hurting you. So that's kind of how this thing goes. So the relative intensity is in micropascals, a pressure unit. So a pin drop is very small. That's 10 to the 0 power. A whisper is about 100. Normal conversation, that's about 1,000,000. A blender, that's getting up to, I want to say 10 billion. A jet engine's about 10 trillion micropascals. So every time you go up 1 decibel, you go up a power of 10. So each decibel is 10 times louder than the last decibel measured. Earthquakes work the same way. We'll talk about the Richter scale in a minute too. So let me just jump to the graphing version, and then I'll come back to why in the world we have this, why it's needed. So if I try to graph 20 decibels, okay, well that was about 100 micropascals. Okay. So if we keep going on a normal scale, this would be 200. Actually, I'm going to slide that 100 down to there. There we go. So this would be 200, 300, 400, 500, and so on. Well, 40 is going to be about 10,000, so that's way up there. Maybe I'll try 30, see if I can fit it on the scale. 30 is going to be about 1,000, so that's already off the scale. It's kind of awkward. Maybe I'll try 10 decibels. That would be 10 to the first power. That'd be way down here. What you're getting is something that's so spread out, it's really impractical to put it on a graph. And no matter where you're looking, the graph is meaningless to you. It really can't convey much information. So that's why we come up with this logarithm scale. It's a way to take things that are just incomprehensibly far apart from one another and put them into a more linear system that we can think about. So rather than, say, 10 squared, we say 2.0, or sorry, the way the decibel scale goes is it's basically times 10. So that power times 10. So 10 squared would be 20 on the decibel scale. Conversations, 10 to the 6th micropascals, that'd be a 60, and so on. So that's what it does. It's a way to turn this into a more linear way of thinking. There's not really much to do on this first example. It's just kind of for informational purposes. It kind of goes back into what we just did on that decibel chart. So let's say you've got a 60 decibel conversation. So that means the intensity is 10 to the 6.0. That's just the way the decibel number is given. They take that power of 10 that the actual volume is, the actual pressure of the sound is, and multiply that exponent by 10 just to make it a nice number. And so that 10 to the 6th power will be 1,000,000. So again, micropascals, because that's the pressure unit that you're in. So just put it as a math statement, 10 to the 6th power would be 1,000,000. So here's the catch. When we're given how loud a sound is, they always tell us it's so many decibels, 60 decibels in this case. But instruments can't really measure that. That's a human way to interpret sound or how loud it is. What instruments can actually measure is this amount of pressure. And like a seismograph, the amount of distance the ground actually moves, that you've probably seen those little needles on the paper moving. That's what our instruments can measure. How much pressure actually hits something that's measuring sound. How much the ground shakes and actually moves. that's what can be measured. So that's where we get this trick, or get this problem we have to get around, is there's a very big difference between a whisper and a jet engine. I mean, so big that we can't even put them on the same graph. It wouldn't even make sense, and that's why we come up with this way to get around it. So here's one that's actually more like what would happen in the real world. So let's say a conversation has an intensity of 49,387, kind of a real number. So that means to get the decibel number, we need to know 10 to the what is 49,387. You can play a game with this and guess the x, which that's what honestly people had to do for a long time before this was developed. 10 to the 5th power would be 100,000, and 10 to the 4th would be 10,000. So somewhere between 4 and 5 for the exponent. And again, you could play around with that, but it's kind of an indirect way to go. So that's where logarithms come in. What we can do is log, it gives us a way around, or how to undo this process. It's the opposite of an exponential. So you take log of the base, this is base 10 raised to something. Take log base 10, that's how we would say that, of this big number. And that tells us the exponent. So let me calculate it out, or if you want to pause here, probably a good time for you to try it, see if it works out. In your calculator, you don't have to do base 10, you just hit log, and it's going to do that for you. So maybe pause and try it, and then I'll show you the answer in a second. So just to show you how it works, you hit the log button, and eventually we'll get into other bases besides 10. I'll show you how to do all that. But for log base 10, it's just kind of understood because we're in a base 10 system. And we're taking log of 49,387, so 49,387, and 4.69367, so about 4.7, which means if you're talking decibels, that's about 47 decibels. Now to check to see how you did, or if the answer makes sense, so 10 to that power right there should be 49,387. I'm going to try the rounded off version just to see how close that is. And it's pretty close. And the more decimal digits you use, the more accurate it's going to be. But for what we're doing, I think 4.7 is probably good enough. I'll put a few more just to see if that's better. That's a lot closer, but I think rounding to one place for now, that's probably going to be good enough. So that real life example leads us to here. Logarithms and exponential functions, they're inverses of each other. So just keep that in mind. One undoes the other. And when you're doing your algebra, that's where they exist. They exist to help you find the exponents if you have an exponential equation and your exponent is a variable. That's why a logarithm exists in the first place. So writing exponents as logarithms, there'll be a few of these just to make sure you get the idea. And let me do a shade so I don't overwhelm you here. So the number that's getting raised to a power, that's your base, which you know what the power is. And for lack of a better term, I'm just going to call that the result. Okay, so 2 to the 3rd equals 8, probably a pretty straightforward statement. I want to focus on the logarithm part because that's kind of the maybe not fully new, but probably needs to be a revisited idea. So log base 2 is kind of written down below it a little. That was your base, so log base 2 of 8, because that was the result, equals the power. So again, logarithms are used when your exponent is the thing you don't know. When your exponent is the variable, that is the purpose of a logarithm. That's when you're going to be using it. So just to read it one more time, you would say it log base 2 of 8 equals 3. And a big point that I'm going to emphasize probably every lesson in this whole chapter, a logarithm is an exponent. In the end, whatever you do with a logarithm, that answer to a logarithm is an exponent, a power. And when you try to learn all these rules that are coming up, we'll start a few of them today, but as you learn these exponent or these logarithm rules, you'll see that they actually follow the exponent rules, and that'll make them a lot easier to remember. And then let's just do a quick example of taking an exponential function or statement and writing it as a logarithm. So 2 to the 5th power is 35. The base would be 2 here, so log base 2 of the result, 32. Is the exponent 5. A logarithm ultimately is the exponent. So again, the way you read it, log base 2 of 32 equals 5. All right, let's run through a couple basic rules that are going to come up throughout the chapter. Now again, in this class, it's not that you can do something, it's why can you do something? How does it work? And making sure you understand that. So you will need to make sure you understand how to derive these formulas. And you'll be asked questions on the homework that use these rules. So one of the first basic rules is if you have log base something, and the base is the same thing as what you're taking the logarithm of, those basically cancel one another out and you're just left with the exponent. That's the rule, but we need to make sure we understand why it's working. So I'm going to prove both of these basic rules for you. The first thing, I'm just going to kind of give you this to start off with and let you think about it. So let's let this left side right here equal something. Let's say I don't know what it equals. I don't know that it's x, but it's got to equal something. So I'm going to say log base a of a to the x is n, some number. And I said other than x because I'm just saying I don't know what this is right off. So some number. Okay, so let's think about how we could rewrite this as an exponential function. Well, if you take the base to the exponent, that would be a to the n power equals the result part here, so a to the x. Well, there's probably not a lot more work to do because if they have the same base, then these exponents would have to be the same. Just sort of not a counterexample, just an example. If I had 5 squared equals 5 to the n, there's only one thing n could be, and that's the same number as what's right here. So hopefully that's convincing. There's really not a whole lot to show there, but the only way this is going to work out to where these are the same overall answer is if these exponents turn out to be the same thing. And since n has to be equal to x, therefore, we know that original statement is true. Log base a of a to the x. I made up n, but I proved that n has to be x, so as a result, that statement has to be true. Okay, something that should have came up in Algebra 2 is called the change of base formula. You can do this stuff in the calculator, but there are going to be some times I don't let you use it. So if you're going to do some of these logarithms by hand, they're a little more tricky. A lot of times this will be the way to go. And you'll see on the homework examples, you'll see kind of some places to use this. In calculus, there are some places where you can't really use a calculator that this is going to be really helpful. So that's kind of where it's going. Just keep in mind this is going to be really helpful for calculus next year. The way this change of base formula works, just to refresh you say log of whatever your new base is, usually 10, but not always, but you say log base 10, for example, of x, and you divide it by log base, the same thing, of base 10 of whatever this base was. So that's kind of how you work that out. So I'm going to start off my proof the same way as before. I'm going to say, I don't really know what it equals. And really, when you're doing proofs, you start with the beginning, or in this case, one side of your equation. You start with one side and just assume, I don't know what the other side is, and you work it out till you confirm what it has to be. So let's say we don't know this piece to be true. Let's say log base a of x equals something. Let's start there. So let's say log base a of x equals n. So if log base a of x is n, we could write this as an exponential and say a to the n power is x. And then suppose I want to introduce a new base here. So I'm going to call my new base b, and I'm going to take the log base b of each side. It's an equation, so I can do whatever I want as long as I do it to both sides. So I'm going to take log base b of both sides. So that means I have log base b of a to the n, and on this side log base b of x. So again, I'm just, at this point, just assume, because I can, I'm going to take a new log base b, of both sides, because I'm allowed to do whatever I want to both sides, so I'm going to try that and see what happens. Now, I'm going to kind of get ahead of myself a little bit here. I'm going to use a rule that we haven't proved yet, which is kind of something I don't usually like to do, but you will prove this rule in the next section, so for now, just kind of accept that it can be done, and know really soon you'll be able to prove why it can be done. But there is a rule that says if we have this situation right here, log base b of a to the n, that this exponent actually can come out front. So that one can be rewritten n times the log base b of a. Now that's some magic, but you will get an explanation and a proof of this really soon. Log base b of x is going to be staying the same on the other side. And now I can just do a little bit of algebra. Since it's n times this logarithm, I can just divide this piece off on both sides. And hopefully it's starting to come into place now. So that would divide out, n would equal log base b of x, log base b of a. Well, that's what we originally said that it had to be equal to. So since log base a of x had to equal something, and we proved that the something it equals to is what we just said, I won't say it all again, that's it. That proves that that formula has to work. Let's wrap this up with a couple of examples. So suppose I want to do log base 5, 78,125 equals x. This is one that you could do by hand, but you have to sit down and figure out powers of 5 until you got to here. And that's not really something I'm going to ask you to do by hand. That's getting to be a little big. I don't expect you to know how many times you multiply 5 by itself to make this happen, especially if it comes out to not be a whole number, if it comes out to be a fraction. So let me show you where the change of base formula comes in handy here. So what I can do is take log base whatever, and base 10 is probably the most easy thing to do here. So log base 10 of the result divided by log base 10 of the original base, and that'll give me my result. And I can just do that in the calculator. So log of 78,125 divided by log of 5. And I'm just saying log because it's base 10, it's understood. And the change of base formula lets me do that. And you get 7. So it turns out 5 times itself 7 times would make this true. And I'm going to go ahead and show you an additional shortcut. Because if you're allowed to use your calculator, and in some parts of these assessments I will let you do this because it's really your ability to do this particular problem. I don't care if you use the calculator. There's going to be some more specific skills I'm going to ask you to do without. So I'll just show you how to do this really quick. And you may already know, if you've got an 84 or more advanced calculator, this will work, or we can at least update it to make it work. If you have an older calculator or maybe a different brand, you may have to do change of base. But if you've got this, the 84 or better, if you do alpha and window, which is F2 menu, and pull up option 5, then I can say log base 5 of, and it was 78,125, and we get 7 that way. Now this example, I do want to see you do this by hand, because this is a place where change of base formula comes in really handy. And sort of a clue, we're taking log base 8 of 32. If you think about 32 and 8, they're both, they're sort of special numbers because they're powers of 2. So if I could think about a base to take, a number that I could raise to a power to make these, it would be 2. And if you're not really sure right away why that works, or you don't see that, here's something you can try to kind of start thinking about it. If you take 32 and break it down with prime factors, you'll see it breaks into 5 2s. And we could have also done that with the 78,125 on the last one, but again, it's not a big deal. Now if you take 8, 8 breaks into 2 times 2 times 2. So both of these numbers are purely powers of 2. So that means that 8 is 2 cubed. I'll go ahead and write that because it's going to come in handy. 32 is 2 to the 5th. So again, I'm going to go ahead and just kind of write those up because those will come in handy later. So if I want to do a change of base formula, I mean, I don't know what power of 8 makes 32. It's not going to be pretty because 8 squared is 64. 8 to the first is 8, so it's somewhere between 1 and 2, but it's going to be a tricky thing to figure out. But what I can do is log base something else of 32, and I'll put the something else in a second, and then log base something else of 8. Well, again, I can do log base 10, but I would pretty much need a calculator for that, because unless you can tell me what power of 10 makes 32 and what power of 10 makes 8, that's not something I expect you to have just kind of off the top of your head. But 2, we know that these are powers of 2. So if we made the base 2 for both of those, this becomes something you could do by hand pretty easily. Now, if you're not thinking in logarithms yet, that's understood. What you can do kind of off to the side here, let's just call this a little scratch work area. So let's, kind of like the proof, log base 2 of 32 is something. And if you rewrite that as an exponential, 2 to the n is 32. You can probably handle that in your head pretty quick. And if not, we did a factor tree already, so 2 to the 5th is 32. So that tells us that this top number, this logarithm, has to be 5. And you can do something similar for the other one. You could say 2 to the something is equal to 8, assuming this equals n. And we already know that 2 cubed is what equals 8, so n would have to be 3 there. So there's a fairly quick way to get your result. 5/3, that's what you should end up with. And that would be something, again, I expect you to do without a calculator. So now let's graph y equals log base 2 of x without a calculator. My advice with these is to do something a little strange, but it seems to work pretty well. Rewrite this as an exponential. 2 to the y equals x. 2 to that exponent equals this result. Now what that's going to mean is you need to kind of plug in values of y to get the x, which is really bizarre, not truly how a function works, but as far as making a graph, this is a pretty good way to do it. Another thing you can try, that most people usually get to a point where they can handle this by the time they take the test, some people sooner, plug in actual powers of 2 for x. So you can plug in 2, 4, 8, 16, and so on for your x value and see what happens. That's pretty much what this is going to do for us anyway, though. So I would like to get a couple of negative values and a couple of positive values. I'm going to use my classic 5, negative 2 to 2. So if I were to put in negative 2 for y, I'm kind of going backwards here. If I put in negative 2 for y, 2 squared is 4. Actually, let's start with a positive end. 2 squared is 4. 2 to the first is 2. 2 to the 0 is 1. All right, so 2 to the negative 1 would be 1 over this, so 1/2. 2 to the negative 2 would be 1 over this number, so 1/4. And there's a quick way to generate some numbers that are going to go in here. So again, the other way to think about it is just pick things you know are powers of 2 and plug in right there for x. So before I put these on the graph, let me ask you something, make sure you're kind of following here. A logarithm is the inverse of, and in class I can get you to answer that question for me. The logarithm is the inverse of an exponential. So exponential should probably go through 0, 1. It probably looks something like this, an asymptote at y equals 0. So think about how aspects of the original show up on the inverse, and then we'll be looking for those things to show up. So I'm going to say them in words right now. Hopefully you can kind of think about this. There's 2 key things that ought to be showing up on this graph. If 0, 1 was on the exponential graph, 1, 0 should show up on this logarithm graph. And if y equals 0 was an asymptote on the original, then x equals 0 should be an asymptote on the logarithm graph. So let's make sure that happens. If I put in 1/4 for x, I get negative 2 for y. It's kind of weird, but that works. 1/2 for x, and I get negative 1 for y. I'm just saying these are weird x values to plug in. 1, 0, there it is. That was something I expected to see. It looks like the asymptote's probably happening too. 2, 1. Finally, 4, 2. So if I go to graph this, it's going to look something like that. And if you want to go one more, if you put in 8 for x, 2 cubed would be 8. So 8, 3 should be on there as well. When you graph these, though, you do need to show me that you realize this is an asymptote. So just be sure that you are putting that on your graph. Now, I just want to quickly compare this to what you're going to see in the calculator, because this is a key thing I want to make sure that you're familiar with. So one more time, when you graph this, you should be showing me there's a vertical asymptote right there at x equals 0. If you don't include that, I am going to take off. It's really important you realize that's there for a logarithm. And you want to be really careful when you put these in the calculator, because I'm going to show you a square root function compared to a logarithm function here. And the blue is a logarithm. The red is the square root. They both look like they just sort of start off at a certain point down here and just go from there. The difference is the square root function does that. It has a definite starting point, and from that starting point it kind of comes into existence and goes along. That's because square root function is the opposite of a parabola, so you're seeing half of a parabola on that red graph. The other part would be down here, but it would have a vertex at that spot. A logarithm, it's not doing that. Even though it looks like it kind of begins its existence right here, it doesn't. The calculator just ran out of pixels. So it has an asymptote at x equals 0. It just, again, it ran out of pixels. If it tried to do the next x value that it could calculate, it got an error. So that's what's going on. If you zoom in enough, you'll be able to see this go all the way down, but you have to zoom in a whole lot. So just make sure you do realize that this logarithm has an asymptote, even though it's not showing up on the graph. Last example for the day. And I just want to go over what this means. It's actually pretty simple to do. Write ln3 equals that decimal number. So usually when I assign this in class, I like to kind of just see what happens, but I figured I'd go on and show this to you now. Ln it's kind of its own thing. It's what it stands for is natural log. And you've already dealt with that number a little bit. It's that ratio, it's that natural ratio that shows up constantly, except it's irrational. It's E. So it turns out that E shows up so much in real life examples that it has its own designation. And if you go high enough in math, when you say logarithm, you're typically talking about what we call the natural log anyway. The log log, you don't even deal with that most of the time because this shows up so much. So anyway, when you see ln, what that means is log base E. So to rewrite this, you're really saying log base E of 3 is that number right there. And that's the key thing I want to make sure you're aware of. It did say to rewrite that, so e to this power would equal 3. But that's the key. I want you to understand that ln means natural log, and it comes up so much, this log base e, it comes up so much, it has its own designation, and it even has its own button on the calculator right below log. It's ln for natural log.